All right, so on number 8, what we're going to do is we're going to create a triangle because I'm a visual person and I like to look at things. So I know that tangent of an angle is always the opposite side over the adjacent side. All right, and I also know that they're telling me that tangent is positive, right? So that's either in quadrant 1 or in quadrant 3 based on what we talked about the other day. All students take calculus, right? I think that that's going to matter later. I don't think it's really going to matter that much in this lesson. I think we're doing all of these in quadrant 1. But later on, we'll have to make a decision as to which quadrant it's in. But they usually give you a second piece of information so that you can make that decision. All right, so you'll have more than one piece of information. So we're going to draw a triangle. And I'm just going to label one of these angles as theta. It doesn't matter. I always do this inside corner because if you think about a unit circle, that's always the angle we're looking at is this inside corner. So the opposite side of that angle is 1. I know that the hypotenuse is across from the 90, so that would be this side. And then I know that the adjacent side is 3. Now, if I'm wanting to figure out anything other than cotangent, so they're asking me to figure out secant, I have to know what the hypotenuse is. And I don't have a special right triangle for I don't have a Pythagorean triple for 1, 3, and whatever is here. Just like we were talking about the other day, I was like, if you have a leg that's 3 and a leg that's 4, then the hypotenuse is 5, right? Or if you have a leg that's 5 and you have another leg that's 12, the hypotenuse is 13. Like those are just some Pythagorean triples that you can just memorize. This is not one of those. So we're actually going to have to do the Pythagorean theorem to figure out the hypotenuse. So remember, to figure out the hypotenuse, you're going to end up taking the square root of your 2 legs added together squared. So that would be the 1 squared plus 3 squared. Now, I would do this in the small calculator because it will reduce the root for you. This is actually going to be 1 plus 9, which is 10. So I get the square root of 10 as my hypotenuse. So now that I have all of the information, all 3 sides, I'm going to do part A, cotangent, which that one's easy because all I have to do is take tangent and flip it. So, oops, not tan, cotan. So cotangent of theta is equal to, I'm just going to flip this, 3 over 1, which is just 3. Then they want me to find secant. Well, I know that secant is the inverse of cosine. So I'm going to find cosine, and then I'm going to flip it. So cosine is adjacent over hypotenuse. So that would be 3 over the square root of 10, right? But we're going to flip it and do it backwards. So square root of 10 over 3. All right, so I know that sine is 1 over 4, so I'm going to draw my triangle. Sine is opposite over hypotenuse, so the opposite side is 1, and the hypotenuse is 4. So to find a missing leg, we'll just call it A, you're going to take the square root of your hypotenuse squared minus the leg squared. So if you're looking for the hypotenuse, you add the leg squared and do the square root. If you're looking for a leg, you do hypotenuse squared minus the leg squared. So that gives you 16 minus 1, so square root of 15. That is this leg right here. Now I can figure out what all the things are. So I know that the inverse of cosecant is sine, right? So if I want cosecant, all I have to do is flip sine. So instead of 1 over 4, I have 4 over 1, which is just 4. Cotangent is the inverse of tangent, and I know that tangent is opposite over adjacent, so that would be 1 over 15, but I'm going to do it backwards because I'm looking for cotan and do square root of 15 over 1, which is just square root of 15. Okay, there's a couple of different ways that you could actually do this one. They're wanting you to use the identities where you're taking like the 90 minus theta. So those cofunction identities, if you're looking at this, this is sine of, this is 90 degrees, right? Pi over 2. So 90 minus theta or whatever, this would be your complementary angle, right? They're saying if I take like the sine of 60, for instance, let's say this said sine of 60 is equal to something, right? You have to think of this 60 as being this part right here, right? That would be 90 minus 30, right, is 60. That's 90, and I've put a number in here so that it equals the 60 that's right here. So 90 minus 30 is 60. This represents the theta, right? So when they say, so that would be equal to cosine of theta. Well, your theta is 30, right? It's kind of like a formula thing. So this side represents sine of 90 minus some angle, and that's equal to cosine of whatever angle that was. So like if you're looking at this right here, this part represents 90 minus some angle, right? Well, what would I have to take from 90 to get the 60? 30. So the angle is 30. And if you look at your cofunction identity here, if you have tangent of something, that's equal to cotangent, right, of that angle. So this would be equal to cotangent of 30. Now, they didn't give you that one here, right? We can actually figure that out by looking at the thing. So I'm going to do this one in a second. This one, if this was 90 minus something is equal to 30, the something would have to be 60, right? And if you look at your cofunction identity, I'm doing sine, right? Sine of something is equal to cosine of the angle. So if this equals cosine of the angle I had to subtract from 90 is what it's saying. So cosine of 60. And what is cosine of 60? 1/2. So this one, the angle would have been what? The angle you subtracted from 90 would have been 60 again, right? And if you look at those cofunction identities, you're doing cosine, and it's equal to sine of that angle that you were subtracting from 90. So sine of 60, and they told you that sine of 60 is square root of 3 over 2. Sine, not cosine. All right, and then cotangent, again, the angle would have had to have been 30, right, that you subtracted from the 90 to get the 60. And if you look at your cofunction identity here, cotangent of that would be equal to tangent, right? Tangent of the 30, correct? So these, we're going to have to do a little bit of, thinking. I think this is a really hard way of doing these, but I wanted to show it just because. Tangent of 60, okay, if you grab your unit circle, if you look at your unit circle, all of these could have been found by looking at the unit circle, correct? Like sine of 30, it would have been easier probably for me to just go to 30 degrees and locate the sine, which is the y value, right? And it's 1/2, right? Cosine of 30, again, it would have been easier for me to go to 30, look at the x value, right? So if I want to find tangent of 60, I can go to 60, and I know that I have to take the y value and divide that by the x value, correct? So square root of 3 over 2 divided by 1/2, which is just going to be square root of 3. And then cotangent of 60 is the same thing as the tangent of 30. It really doesn't matter which one you look at. Like if I wanted to do cotangent of 60, I could do that. But if I wanted to do tan of 30, I mean, it's the same thing, so it doesn't matter. So I'll go do the tan of 30. I would take the 1/2 and I would divide it by the square root of 3 over 2, which is going to give me square root of 3 over 3. So on number 11, I know that sine is the inverse of cosecant. So if I want to know the sine, I would literally just flip my cosecant, which in this case is 3 over 1. So I would flip it, and that's 1 over 3. I know that cosine is the inverse of secant. So I would flip this one, but I'm going to have to do a little work because if I flip it, I have this, right? So I can either just plug that in the calculator and let it do it for me. If I do it by hand, just so you know, I'd multiply by the square root of 2, right? So I would get 4 square roots of 2 on top. And then on bottom, the square root of 2 times the square root of 2 is just 2, and 3 times 2 is 6, but I would have to reduce to by 2, right? And get 2 square roots of 2 over 3. But your calculator will do that for you, the small one. All right? I know that tangent is sine over cosine, so I can literally, I know sine and I know cosine, so I can take the 1/3 and divide that by 2 square roots of 2 over 3. I'll have to flip that, so it would be 3 over 2 square roots of 2. The 3's cancel, and then I'm going to have to get rid of that square root of 2, right? I'm going to multiply by the square root of 2, and I get the square root of 2 over square root of 2 times square root of 2 is 2 times 2 is 4, so square root of 2 over 4. And then here's another one where they're giving you that 90. So if you look at your cofunction identities, remember this pi over 2 is the same thing as 90. So when I look at this problem, they want to know the secant of 90 minus theta. Well, secant of 90 minus theta is the same thing as cosecant theta. So I already know cosecant theta is just 3. So when you see that, don't freak out. Just look and see what it's equivalent to, and then you'll know. All of these, though, you don't have to do them by hand. You can just put them in the small calculator, and it will reduce for you. All right, so we're going to be using those trig identities to transform one side of our equation into the other. Now, this piece of information, remember this represents your angle. They're saying your angle is between 0 and pi over 2. If you think about your unit circle, 0 is here and pi over 2 is here, so that means your angle is somewhere in between here in your first quadrant. All right. Notice, though, there are no equal to's. Are you with me? So it will not equal 0, and it will not equal pi over 2. It's just somewhere in between. So here's the thing. These problems, they're going to come back with a vengeance in the next chapter. And this is where almost, I'm going to say 95% of people struggle in here, is with these. So if you can get a good handle on them, they take practice, okay? Even I was awful at them for a really long time. They take practice. It's almost like a puzzle. So you're trying to get one side, you're going to leave one side alone, okay? This is not like the kind of equation where you move one thing to another side. You will not be changing sides of anything. You're literally just going to rewrite and rewrite and rewrite until you can show that the left side is the same as the right. So usually you're going to start with like the most complicated looking side. So in this case, that would be this side. Your goal is to keep rewriting until you get down to a 1. Then you can say, okay, well, these are equal. So let's think about things that usually equal 1. Like if I take something and divide it by itself, right? So like 7 divided by 7, that equals 1. Okay? If I had like a cosine theta over a cosine theta, that would be equal to 1. Anything over itself, correct? I also am going to think about my identities. So usually you'll use a lot of your tangent identities, you'll use a lot of your reciprocal identities, and you'll use a lot of your Pythagorean identities. Every now and then we do these, but we haven't talked about them yet, so we're not even going to pay attention to them. So if you look at this, I know that 1 can be rewritten as sine squared theta plus cosine squared theta. So anytime I see a sine squared theta plus cosine squared theta, I'm going to remove it and replace it with a 1 because they are equivalent, right? Same thing with like if I see tangent squared theta plus 1, I can replace that with secant squared theta. You can replace things, right, that are equal. Well, we've rewritten all of these, right, in we have 3 different ways of writing all of these. We wrote them all down. So like, for instance, remember we wrote one where we had secant squared theta minus tangent squared theta. If I ever see that, I can replace it with 1. So I'm just going to go through and try to replace and replace and replace until I get the other side showing as equal. So if I'm looking at this, normally you want to start with like taking any kind of trig function you have and writing it with either sine or cosine. So I have a cosine here. Can I rewrite secant using a cosine? So I look at my identities here. I know that secant is 1 over cosine. So I can take secant out and I can replace it with 1 over cosine theta. So now that I've done that, I see that this is over 1, right? And I know that if I'm multiplying fractions, I can cancel diagonally, right? That means my cosines cancel, and all I'm left with is 1. So now I've rewritten this side, and I can show that these two are equal. Now, on part B here, I have 2 binomials, and I should actually multiply those, okay? Because if I go through and try to rewrite all of these, like if I change secant to 1 over cosine, and I change tangent to sine over cosine, I mean, I could do that, but that just seems, then I'd have a lot of fractions, and then I'd still have to multiply, and then I think we would just get annoyed. So we're going to actually go through and multiply this. So I'm going to take the secant and distribute it through the other parenthesis, and then I'll take the tangent and distribute that. So secant of theta times secant of theta would give me secant squared theta. They work just like variables do. And then I have secant theta times negative tangent theta is negative secant theta tangent theta. It's kind of like if this was x times a y, you would just have xy, right? Tangent theta times secant theta is a positive secant theta times tangent theta. It doesn't matter what order you write them in, but I already noticed that I had a secant times a tangent, so I put the secant in front. And then tangent theta times negative tangent theta is negative tangent squared theta. So if you look at this right here, see how these are the same? They're just opposite signs. So this would be like a negative 1 secant theta tangent theta and a positive 1 secant theta tangent theta. Those are going to cancel, right? And now I just have secant squared theta minus tangent squared theta. Okay? Now, once you get some squareds in there, that should kind of prompt you to look at those Pythagorean identities right here. Now, remember, when we rewrote these, we kind of solved for each part, right? So when we solved for 1, we subtracted the tangent squared theta, which gave us 1 is equal to secant squared theta minus tangent squared theta. And isn't this exactly what we have written on our paper right now? That is the same thing as 1. So I can take it out. I'm going to take this whole thing out and replace it with a 1. And now we have shown that the two sides are equal. So I'm going to kind of make you guys struggle a little bit through here. First off, pick the side that looks more complicated, which in this case would be this side, correct? So what I like to do is kind of try to figure out like where I'm going. I want a secant in the end. So let's think about what we could possibly get to get a secant. I could have like a 1 over a cosine, right? Because they're inverses, and that would lead me to a secant. So if I'm looking at this, I'm thinking, okay, I told you guys to maybe start with, if you don't have anything to multiply, you know, like this, you would have to multiply that together, right? You don't have anything to multiply here, like distributive-wise. So write everything in terms of sine and cosine. That's where I would start. So what can I rewrite tangent with? Look at your identities. Usually your reciprocals when you're thinking about writing. You're usually looking at these if you're trying to rewrite one term. So what could I rewrite tangent with that would have sine and cosine? Sine over cosine. So I'm going to replace tangent with sine theta over cosine theta. And then I always like to put the multiplication symbol here just because. And then how can I rewrite cosecant using sine or cosine? Look at your Pythagorean identities. Doesn't have to be both, just one of them. 1 over sine, right here. See how it says cosecant theta is equal to 1 over sine. So I'm going to replace that with 1 over sine. And then what's going to happen right here? Okay, sines cancel, so on the top I'm left with 1, and on the bottom I'm left with cosine theta, and I still have my secant theta over here, right? So remember how we talked about a while ago what you might have right before you get to secant? I'm there, right? 1 over cosine theta is what? It's secant theta. So now I have shown that the left-hand side is the same as the right-hand side. So if you look on part B, see how you have you have the two binomials, right? Notice, you do not have anything that's squared. And usually, we like to have things that are squared if we're going to be multiplying, you know, or replacing stuff when there's extra stuff in there. Like this was just a sine and a cosecant, right? This has like plus 1s and minus 1s. So we definitely want to multiply this. So if I take cosecant times cosecant, that gives me cosecant squared. Then I have cosecant times negative 1 is negative cosecant. 1 times cosecant is positive cosecant. And then 1 times negative 1 is negative 1. And then these two, they're the same but opposite signs, so they're going to cancel. So I'm left with cosecant squared theta, and then I have that minus 1 at the back. I'm still trying to figure out if that's equal to cotangent squared theta. Now see how I have a squared term and then the 1? That should immediately tell you, hey, you need to look at your Pythagorean identities. So I have cosecant theta minus 1. Cosecant squared theta minus 1. Now, do you see how in this Pythagorean identity, it's the only one that has the cosecant, right? None of the others do, so I'm going to look at this one. It also, if you'll notice, has a cotangent, and isn't that where we're trying to get? Okay, so that should lead you to say, okay, this is probably the one I'm using. And if you'll remember, when we solved for cotangent, we subtracted the 1, right? So cosecant squared theta minus 1 is the same thing as cotangent squared. So I can remove the cosecant theta minus 1 and replace it with cotangent squared, and now I have reached where they are equal. All right, 14. Again, we're verifying again. Start with the side that is the most complicated looking. That would be this side, right? So everything is already written in terms of sine and cosine, but I don't like this fraction, okay? And I believe I've mentioned this before, but maybe I haven't, so I'm going to mention it now just in case. These all work no matter what the power is. Like, on your Pythagorean identities, I can't change these squared. Like, that's just what they are, right? But, like, if I have, like, a tangent squared theta, that is the same as sine squared theta over cosine squared theta. Or if this is, you know, cotangent squared, that's the same thing as 1 over tangent squared. So the powers just match, right, on any of these. So on any set of these. I feel like I mentioned that, but maybe I didn't. So whenever you are doing these, first off, 1 over sine squared would be cosecant squared, right? It's still the inverse, just keep the sign. So I'm not doing anything with the left side, just this side. So I'm going to replace that with cosecant squared theta. And the only reason I'm okay with doing that is because I see that I have this minus 1 right here, which means that I'm probably going to have something up here with a squared. And I know that because when you look at your Pythagorean identities, they all have 1s and squareds, right? All right, so if I'm looking at this, is there a replacement for cosecant squared minus 1? That also has a cotangent, right? It's the same one. So when I subtract that 1 right here, cosecant squared theta minus 1, that's the same thing as cotangent squared theta. So I can take out the cosecant squared theta minus 1 and replace it with cotangent squared theta. And then I have shown that they are equivalent. All right, so on number 15, the more complicated side would be the left side. Do you see any terms that have a squared? No, not on the left, right? Do you see anything that you need to multiply? Well, but remember, I'm not moving secant to the other side. It has to be something that's just done on this side. You're just simplifying this side. You never move, which is kind of a hard concept because that's what you've done for the last, like, 3 years, right? With equations, you move stuff around. Here's the thing. I know that if I have 2 terms on top and 1 term on bottom, that just means this term divided by this and this term divided by this. So I'm going to split this off into 2 separate things. Secant theta divided by secant theta, and then you've got that minus sign, and then the cosine divided by secant. What is anything divided by itself? So this is a 1. Now, I can't divide cosine and secant, but I do know that secant can be rewritten with a cosine, right? So how can I rewrite secant using cosine? It's 1 over cosine. All right? Now, we don't keep fractions inside of a fraction, right? So I'm going to take And I'll keep the cosine that's on top, but then you got to flip the bottom, right? So I'm going to multiply by cosine theta over 1, which is just cosine, right? So I'm literally just flipping this bottom fraction. And when I take cosine theta times cosine theta, what does that give me? Okay, a cosine squared theta, right? Now, look at your Pythagorean identities because now you've got a 1 and a squared term. Oops, wrong thing. So if you look at your Pythagorean identities, 1, if I were to subtract the cosine squared, right? 1 minus cosine squared theta is sine squared theta. So I can take that and replace it with sine squared theta. And what was the other side? Sine squared theta. So I have shown that they are equivalent. Okay, so angles of depression and elevation, this is not new to you, okay? So here's the thing. Think of this as like eye level. If I'm looking out and then I look up, that's the angle of elevation. So from eye level up. If I'm looking out this way, like maybe I'm like at the top of a tower, and then I look down, that part is my angle of depression. So from where I was looking straight to where I'm looking down, so the middle part right there, okay? A lot of people want to put it like right here. I don't know why, but it's right here. So I like to draw pictures. This is, oh, that should be feet. A survey is standing 50 feet from the base of a large tree. There's my beautiful tree, and I have a dude. He's standing 50 feet away. So this would be 50 feet, right? The surveyor measures the angle of elevation to the top of the tree as 71.5 degrees. All right, so to the top of the tree, angle of elevation. So that would be from straight, looking up. That would be this angle right here is 71.5 degrees. How tall is the tree? So that would actually be this side of my triangle, correct? We'll just call that X. Now, you did these in geometry, okay? So if this is the angle that you have, then you need to identify what side the 50 is and what side the side you need is. So compared to this angle. So this angle is my angle of elevation. Across from that, this side would be the opposite side. That's the side I'm trying to find. And then this side would be the adjacent side. I know it's not the hypotenuse because this is the 90, right? Which means this is the hypotenuse. So which trig function deals with the opposite side and the adjacent sides? Think about your SOHCAHTOA. The tangent, right? So I'm going to do tan of that angle right there, the 71.5, is equal to the opposite side, which is x, over the adjacent side, which is 50. Now I just have to solve for x. So I'm going to multiply that by the 50 to get that off the bottom. So all you have to do is plug in 50 tan 71.5. What's the one thing you need to make sure, though, about your calculator? That it is in degree mode, right? Because you're taking the tangent of a degree. So when you plug that in, you should get about 149.43, and this is feet, right? So that's about how tall the tree is. All right, you are 200 yards from a river. So here's the river. I'm 200 yards away. I guess I'll draw me down here. Here I am. You walk 400 yards along a straight path to the river's edge. this is 400 yards. So this would be my 90-degree angle, correct? Find the acute angle theta between this path and the river's edge. So this is the path, this is the river's edge, so I'm trying to find this right here. So I don't know the angle, correct? But I do know the side that is opposite of that angle, and then this side represents the hypotenuse. So which one of your trig functions deals with opposite and hypotenuse? Sine. So I know the sine of my angle is equal to the opposite side, which is 200, divided by the hypotenuse, which is 400. Now, do you remember how to solve for the angle? You have to do the inverse. So I'm going to do the inverse of this side and the inverse of this side. This is just when I don't know the angle, right? So the sine inverse and the sine cancel. And so in my calculator, I'm just going to be plugging this in. And actually, if you wanted to reduce that, you could, right, to 2 over 4, which is the same thing as 1/2. And another way of thinking this is, what angle has a sine of 1/2? And so that's going to be kind of interesting. So your angle is, now to get the sine inverse, you would press the second button and then the sine button. And that gives you 30 degrees. And this is going to be helpful information for later. If you think about your unit circle, like I said, this means what angle has a sine of 1/2? 1/2 is the y value, right? Here's the sine of 1/2. What's that angle? 30 degrees. But if you just plug that in your calculator, you get what the angle is.